Hello everybody and welcome to Chapter 3, where we'll be studying eigenvalues and diagonalization. Notice that towards the end of this chapter, we'll see our first two big applications of linear algebra. But first, we need to talk about eigenvalues and eigenspaces. We'll do it this is going to be for matrices, and then we'll see how to generalize this to eigenvectors and eigenspaces for linear operators, so linear transformation from a vector space to itself. And then we'll see how to use this to diagonalize both a matrix and a linear transformation. And we'll apply that principle to study differential equations of certain types and to study Markov chains. All right, so let's get started. Let's start with eigenvalues and eigenspaces. Here's our goal. Given a square matrix A, determine the geometry of the linear transformation T of A from Rn to Rn using algebra. All right, section 3.1.1, I'm going to define eigenvalues and eigenvectors. First, let's do an example to see why we're after something like this. All right, consider the matrix. And here's my matrix, minus 15 over 17, 8 over 17, 8 over 17, 15 over 17. It looks like a pretty bad matrix. I want to figure out what this matrix does geometrically. So describe the geometry of the linear transformation T of A from R2 to R2. That's a linear transformation that multiplies vectors of R2 by A. All right, so to do this, the first thing we would look at is we want to look at where it sends the two basis vectors and hopefully get a sense of what the linear transformation is doing. So TA of E1, that's A times E1 all right, so times 1, 0. I mean, that will just give you the first column. All right, so E1, which is this vector, is sent to almost minus 1 and plus something like this. All right, we now need to look at T of E2, and then minus 15, 17, 8 over 17, 8 over 17, 15 over 17, 0, 1. That's going to give you the second column. So 8 over 17 and 15 over 17. Right, so if I look at this, 8, 15, it's going to give me something here. 8 and 15 a bit higher than it is wide, something like this. All right, so from this, can you tell what TA does? Couple things I notice. I notice that the vectors are not stretched. They still look like they have length 1. In fact, I could compute it and check that they have length 1. Second thing I notice is they're still at a right angle. All right, so something that doesn't change angles and doesn't change length, that looks like a pretty nice linear transformation. Because the order, I have green, then purple, green, because the order is flipped, I would say this could be some sort of reflection. And if I wanted to be a bit more daring in my prediction, maybe a reflection around somewhere here. But again, it's not convincing. Maybe. All right, so it's not 100% clear. I have some ideas, but it's not 100% clear. Now I'm going to use divine inspiration. I'm going to see what happens to these two seemingly strange vectors. All right, so I'm going to look at TA of 1, 4 That's minus 15, 17, 8, 17, 8, 17, 15, 17 times 1, 4. So I'm getting minus 15 plus 32 over 17. That's just 1. Then I'm getting 8 plus 60 over 17. That's 4. All right, this is pretty cool. It's pretty cool because that vector is sent to itself. So 1, 1, 2, 3, 4. That vector one, 4 is actually t of itself. All right. What about the second one that we are given, minus 4, 1? Then if I multiply that by a, I get 60 plus 8 over 17. I get 4. And I get minus 32 plus 15 over 17. I get minus 1. All right, so now this one's tiny bit tricky. So minus 4, 1. That one is sent to 4 minus 1. And if you notice, that angle here is right angle. So the vector 1, 4 is not moved, so I'm going to not sure why there's an arrow. All right, I'm going to look at the line here. So I'm going to look at this line. And TA is a reflection across L, which is the line, well, the slope is 4, so 4x. So by looking at these two special vectors that are sent to, well, 1, 4 is sent to itself, the other one is sent to minus itself, I can really tell what the linear transformation is doing. Right? So let's see, the vectors 1, 4 and minus 4, 1 are called the eigenvectors of T. So I don't want to use divine inspiration because I don't think it's going to come in at the right time while we're doing an exam. So we'll learn how to use algebra to find these eigenvectors.